Let's now consider Born-Haber cycles. Now, lattice enthalpies can't be measured experimentally, and so we calculate these values using the Born-Haber cycle. I know Born-Haber cycles can look pretty scary, but they're simply building on everything you guys learned in the first year related to Hesse cycles. I've just dragged in some Hesse cycles here to remind you that in the situation when you can't measure the direct enthalpy change, remember you can follow an alternative route to arrive at your answer, and it doesn't matter what route that is, as showcased here. And you're going to use that theory when it comes to the Born-Haber cycles. Now, unfortunately, the worst thing about this topic is the list of definitions. And I can't believe I'm saying this, but you will need to know these all off by heart. And not only will you need to know them off by heart, but you'll actually have to apply them in order to construct the Born-Haber cycles. So the mean bond enthalpy is the energy required to break a covalent bond in a molecule, averaged over a range of compounds. The enthalpy of formation, you'll be familiar with, is the enthalpy change when 1 mole of a substance is formed from its constituent elements under standard conditions, with the reactants and products being present in their standard states. Remember that standard conditions are 100 kPa and 298 Kelvin. Enthalpy of atomization is the enthalpy change when 1 mole of gaseous atoms is formed from an element in its standard state under standard conditions. The first ionization energy you'll have met near the beginning of the course. This is the enthalpy change when 1 mole of gaseous atoms each lose an electron to form 1 mole of gaseous ions with a single positive charge. Ionization enthalpies are always positive because energy has to be put in order to pull that electron away from the attraction of the positively charged nucleus. The second ionization energy is the enthalpy change when 1 mole of electrons is this time lost from a mole of singly positively charged ions. So here's the crucial difference here between the first and second ionization energy, as well as the product formed. The first electron affinity is the enthalpy change for the formation of 1 mole of negative 1 minus gaseous ions from 1 mole of gaseous atoms, as shown here. These are always negative as there is an attraction between the nucleus and the electron, meaning that energy is released when the electron is gained. The second electron affinity is the enthalpy change for the formation of 1 mole of gaseous 2 minus ions from 1 mole of gaseous 1 minus ions. So we're just taking that previous step one step further. These are always positive as energy must be put in to overcome the repulsion between the electron and the negatively charged ion. The lattice enthalpy of formation is the enthalpy change when 1 mole of solid ionic compound is formed from its gaseous ions. These are always negative because when the lattice forms, new bonds are formed, resulting in energy being released, which remember is an exothermic reaction. Lattice enthalpy of dissociation is the enthalpy change when 1 mole of solid ionic compound separates into its gaseous ions. These are always positive because energy is required to break the bonds in the lattice. You can see in the instruction here in my revision guide, you always want to look back, you always want to refer to these definitions when working through various questions. Now we're going to draw out a Born-Haber cycle using these definitions to illustrate how it's assembled. So in this example, we're going to be drawing a Born-Haber cycle, and we're going to use that to determine the lattice enthalpy of formation of copper oxide. So I've drawn 2 lines here. This is going to be my start. This is going to be my finish line, the end. Remind yourself of the definition of the lattice enthalpy of formation. It's the enthalpy change when 1 mole of solid ionic compound is formed from its gaseous ions. So that means the solid ionic compound is here, the gaseous ions must be here. And here's my solid product. So that is my lattice enthalpy of formation. So this is in effect my X, my lattice enthalpy of formation. As I previously said, we can't work out this value experimentally, so we're going to have to use a different route akin to the way you were doing the Hess cycles in order to calculate this value. So the next thing to be aware of is down here, you need a way of producing that solid copper oxide but through a different route, and the way to do that is using the enthalpy of formation. So to remind you, that means 1 mole of substance being formed from its constituent elements under standard conditions with the reactants and products being in their standard states. That's why it's so important you know the definition, because that tells me straight away that my copper must be solid and that my oxygen must be in gaseous form and we're producing 1 mole, so that will help me balance my equation here. So that's my standard enthalpy of formation. So now I need to create my alternative route that will take my elements in their standard state to the ions in their gaseous state. And for each step you write down, you're only changing one thing each time. Bear that in mind. So the first thing you want to do is to change the state of the copper. We're only touching the copper in this stage, so we're going to atomize it, which according to the definition means that we're forming 1 mole of gaseous atoms from the element in its standard state under standard conditions. And look, here's an example there. So there's my copper forming a gas, and my oxygen remains the same. My arrowhead points upwards because I'm forming the gas. Make sure you label this. It's the standard enthalpy of atomization of copper. We now need to ionize the copper. Remember that copper forms a Cu2 plus ion, which means we need to effectively do a first ionization of that copper and then a second ionization. So that is our next 2 steps. We form the 1 plus ion initially, keeping the oxygen the same. And here's the electron that we've removed, and we'll label that the first ionization energy. Now we'll do the second ionization. So this time we're forming a Cu2 plus ion. The oxygen remains the same. We now have 2 electrons, and then label it. So just double check, sit back, look, your copper is exactly where it needs to be. So it's now time to turn our attention to the oxygen. The first thing we need to do is atomize it, because at the moment it's O2 and we need to get it as an individual atom. Noticing that everything else remains the same, do label this. It's the enthalpy of atomization of oxygen. And notice, because we had half an oxygen in here, we only create 1 atom. Now we check your definitions. This is when first electron affinity becomes important, because it's the enthalpy change for the formation of 1 mole of negative 1 minus gaseous ions from 1 mole of gaseous atoms. Because it's a negative value, we do need to make sure that line sits lower. I'm changing colour just so it doesn't get too complicated. The copper stays the same, and then the electrons cancel out, so we end up with only 1 E minus. That's your first electron affinity of oxygen. And then our last stage, guys, we're almost there, is we need to do the second electron affinity. Remember, we said it's always positive. And then remember, because we're using that electron, we're adding it to the oxygen to form the O2 minus. That's why it doesn't appear up here. But after all that hard work, we've constructed our Born-Haber cycle. I know it looks super complicated, but just take a step back. What was our first step? It was to atomize and then ionize the metal. Then really the second step was to atomize and then ionize the non-metal. And that's how we constructed the left-hand part of our diagram. I'm now going to add some numbers so you can see how you'd actually carry out the calculation. You would be given these numbers in the question, but I'm just going to add them here. I'm not going to put the units because I don't want it to get too complicated. Remember, I said that this is your x value. So we're going from here to here. But in order to do the calculation, we're going to follow this route this way. Just make sure you acknowledge the signs. We're going against the arrowhead. So it's minus 790 plus 141 minus 249 minus 1960 minus 745 minus 339 minus 155, because that's following the direction of the arrowhead, equals minus 4097. I'll introduce the units, kJ per mole. And remember, your X was the enthalpy for the lattice formation. So what to take away from this? Learn your definitions. Without the definitions, you can't do anything. Put the solid product at the end. Top right, you're going to list the ions needed to make that product. That will be your standard enthalpy of lattice formation. And then here, you're going to construct your Born-Haber cycle, first by atomizing your metal, then ionizing it, making sure the ion formed is your standard ion. Same for your non-metal, you're going to atomize and then ionize, and then just follow the route, making sure you reverse any signs based on which direction arrowhead is pointed. Now they do alter what it is they're asking for. So in this particular example, we're being asked to construct a Born-Haber cycle for magnesium bromide in order to calculate the first electron affinity for bromine. So we've got lots of data here that you'll be familiar with that we're going to use. We're going to start like we did in the previous question by doing the lattice enthalpy of dissociation, so showing the working out for that. Remember, that involves having the solid compound at the bottom. So our first step is the dissociation of magnesium bromide into its ions. So we'll draw the ions up here. Remember, we're forming 1 mole, so that will dictate your ions. Be careful with your arrows. Because they're dissociating, we need to point the arrow in this direction. So this is the lattice enthalpy of dissociation. Before we start atomizing and ionizing the magnesium and then the bromine, the first thing we need to do is do our enthalpy of formation of the magnesium bromide. So we list the elements here in their standard states. Now we're ready to get going. We're going to start by atomizing the magnesium, which means turning it from a solid to a gas. Remember, the bromine remains the same. We only change one thing in each step, pulling the numbers from the table. Next up, we're going to form the Mg plus ion, so the first ionization energy of magnesium. Because magnesium forms 2 plus ions, we need to do the second ionization energy. Don't forget to add your electron. So we form the Mg2 plus ion. Bromine currently remains the same. So that's your second ionization energy. We're all good now for the magnesium. It's time to turn our attention to bromine. Let's atomize it. Just be a little bit careful here. Remember, we're going from that bromine diatomic molecule to 2 atoms of it, which is why we need to double this number here. And then we're trying to form our bromine ion. Check your definitions. You're going with the non-metal, you're forming the negative ion. This is your first electron affinity, and after all, that's what the question's after, so that in effect is your X. Remember, first electron affinities are always negative according to that definition. So that's going to take us from our gaseous bromine to the negative ion. Because we're forming 2 negative ions, we need to multiply that number by 2, and after all, that's our X value. And that explains why we've lost the 2 electrons as we go from here to here, because each of those bromines has gained an electron to form the negative ion. So now we're ready to do the maths element. So we're after 2x. Let's go around this way, making sure we pay attention to the arrowheads. We're going against this one, so it becomes 2 times minus 112, minus 1451, minus 738, minus 148, minus 524, plus 2440. So that comes to minus 645. Divide it by 2. Add your units, kJ per mole, and that is your first electron affinity calculated for bromine. And there's your final answer. This is absolutely a topic which needs past paper practice. We're going to start with question 1, define the term electron affinity for chlorine. Just going to copy in the definition from my guide. So it's the enthalpy change for the formation of 1 mole of negative gaseous chlorine ions from 1 mole of gaseous chlorine atoms. Complete this Born-Haber cycle for magnesium chloride by giving the missing species on the dotted lines, include state symbols where appropriate. It's so great when they do this because they give you lots of clues. We can see straight away here that we've got ions, so we just need to add the chlorine ions in gaseous form. This is enthalpy of formation, so we're taking the elements in their standard states. So magnesium is solid, chlorine, you must remember, is a gas. Following this arrow, we're atomizing the magnesium, we're keeping chlorine the same. Next step, we're doing the first ionization of magnesium, keeping chlorine the same. Make sure you show that electron. Because magnesium forms 2 plus ions, we need to show that through the addition of those 2 electrons. And then next up, we need to deal with the chlorine by atomizing it. We've got Cl2 gas here, but we need to form 2 chlorine atoms. So that's done. And then just to prove, look, we've got our electron affinity. We're forming chloride ions from those chlorine atoms. changing only one thing in each stage. Now we're being asked to use our Born-Haber cycle from part B and the data in that table to calculate a value for the electron affinity of chlorine. So let's go up here, let's label a 2x here. Why? Because we're forming 2 chloride ions. So I'm going to write it here so you can see it more clearly. Let's label the numbers. So this is lattice formation here, minus 2,493. This is enthalpy of formation, minus 642. Here we've got atomization of magnesium. Then we've got first ionization of magnesium, plus 736. Second ionization, plus 1450. And then here we are atomizing the chlorine, plus 121. Don't forget to do that number twice because you've got 2 chlorine atoms being formed. So we're going to head in this direction. Make sure you acknowledge the arrowheads. We're going against this arrowhead. So we do 2 times minus 121, minus 1450, minus 736, minus 150, minus 642, plus 2493. So that comes to minus 727. Divide by 2 to find x to get minus 364 kJ per mole. Let's do this example now for silver fluoride. So in our first step, we're doing our enthalpy of formation of silver fluoride. Remember, we're forming 1 mole, so just be a little bit careful here. Yes, we know the standard state of fluorine is a diatomic gas, but because we're forming 1 mole, we need to put a half here. Then as we move up, we atomize the silver, keep the fluorine the same. Then we do the first ionization of silver, acknowledge the electron, and then next up, we're atomizing the fluorine. Use the cycle in part 1 and the data here to calculate a value for the bond enthalpy of the fluorine-fluorine bond. So this is a little bit confusing. It actually refers to the atomization of the fluorine, but if you're not sure, just fill in all your other numbers and see where your X is. I'll show that that works now. So we know that the enthalpy of formation of silver fluoride is minus 203. We know that the enthalpy of lattice dissociation is plus 955. The electron affinity of fluorine now of minus 348, remember, goes here. The first ionization energy for silver goes here. And then the enthalpy of atomization for silver goes here. Where's our X? We can see it goes here. This is our X value. So according to the direction the arrowhead's pointing, tells us that our start is here, our end is here. Do add these labels if it helps you, and that tells you that we're heading in this direction. Just make sure you acknowledge those arrowheads we're going against. So that's minus 732, minus 289, minus 203, plus 955, plus 348. Put it into your calculator. The answer here is 79 kJ per mole, but do check. Just one final sting in the tail. This is half your value due to that half there, so you just need to multiply it by 2 to get your final answer.